Hello, my name is Ignacio Sirac. I'm a scientist working on quantum physics at the Max Planck Institute of Quantum Optics in Munich, Germany. And I'm representing here the Munich Center for Quantum Science and Technology, in short, MCQST. This is a research and education consortium of the two universities in Munich, the Ludwig Maximilian and the Technical University, the Max Planck Institute of Quantum Optics, the Walter Meissner Institute, and the Deutsches Museum, the German museum. MCQST is funded by the German Science Foundation and composed of about 50 principal investigators and more than 200 students and postdocs in the Munich area working in all areas of quantum science and technology. And on behalf of MCQST, I would like to welcome all the viewers to the first edition of the Munich Quantum Stammtisch. Stammtisch is a traditional and popular term in Germany, especially in Bavaria, the region where Munich is located. It is a group of people who meet regularly around the table with some beverages, typically beer, for socializing, playing cards, and political or philosophical discussions. Stamm means stem and Tisch, table. So Stammtisch exists since the end of the 18th century. At the time, citizens regularly met for social gatherings in inns, wine houses, and coffee houses. In the second half of the 19th century, a Stammtisch typically consisted of local dignitaries, such as the major, doctor, pharmacist, teacher, wealthy farmers. Inviting a stranger to take a seat at the Stammtisch was a sign of extraordinary appreciation. Later on, writers and artists, intellectuals, and people in general were included, and specialized Stammtische were widely spread all over Germany. Now, there are many such meetings devoted to literature, philosophy, German or English culture, and many, many other subjects. MCQST decided to start a series of Munich Quantum Stammtisch and to broadcast it live by our YouTube channels. Just like a traditional Stammtisch, our guests will cover the latest in quantum science and technology in an informal atmosphere. We want to trigger general, non-technical discussions about their visions, perspectives, concerns, and opportunities in the field. Each meeting will have a main subject. Taking advantage of the fact that QAP, a major conference on quantum information science, is being held this week in Munich and organized by MCQST, we decided to devote the inaugural edition of the Munich Quantum Stammtisch to quantum computing under the title Quo Vadis, Quantum Computing. Where are you going? Quantum computing. Because of the present situation, we cannot hold our discussion in person around the Stammtisch, but we are using our YouTube channel. Nevertheless, some of us received some beverages. So I have here mine, beer, and some of our speakers have also their own beverages and are different. So they are not all beers because we are different time zones, and you can imagine that sometimes the beer is not the best thing in the morning. Our guests are coming from outside Munich and world experts in the subject. As in former times, we want to express our extraordinary appreciation for the contributions or the role in quantum computing, but especially learn from them their visions about this fascinating area. Before introducing our guests, let me express my most sincere thanks to Anna Ionescu and Tatiana Will from MCQST, who have planned and organized the meeting, as well as organized some beverages for all the participants. About a year ago, Google announced the achievement of quantum advantage with a quantum computer built with superconducting qubits. This result, together with other ones obtained with other computing platforms like trap ions or Rydberg atoms, have triggered a lot of expectations and hopes, not only in the scientific community, but also in the industry and in the media. However, are those hopes realistic? And even more, will quantum computers revolutionize our society in the next few years? Or will we have to first go through a long quantum winter? What will be the impact in the industry, politics, and society in general? Also, from a scientific point of view, what are the most urgent questions to address? We want to discuss all that with our guests, whom I would like to introduce now. They are all outstanding scientists who have made immense contributions in the field of quantum computing. I will not mention here those contributions, it would take most of our time. However, I highlight just one of their achievements for each of them so that the audience becomes aware of the caliber of our Stammtisch. I apologize in advance in front of all of them in case that the achievements that I mentioned here is not the most significant for them. Before that, I would like to thank them for sharing their time and experiences at different time zones from the US to Europe, Middle East, and all the way to Australia. So let me start with Scott Aronson from Texas University, US. He's a computer scientist and show how with the first generations of quantum computers, one could prove quantum advantage. It is to demonstrate that the quantum computer can solve a problem which is not possible for existing classical ones. Second guest is Dorit Aranov from the Hebrew University of Jerusalem, Israel. She's a computer scientist who showed back in '96 that fault-tolerant quantum computing with constant errors is possible, and our hopes to construct scalable devices rely on her result. Rainer Platt from the University of Innsbruck, Austria. He's an experimental physicist who pioneered and now leads the experimental efforts to build quantum computers with trap ions, and is also a co-founder of Alpine Quantum Technologies, a startup. Michael Luking, University of Harvard, US. He's a physicist, both theorist and experimentalist who had the idea of using Rydberg atoms to build quantum computers, build one, and discover new physical phenomena with such a device. And John Martinez from Silicon Quantum Computing, Sydney, but Australia, and also University of California in Santa Barbara, the US. He's an experimental physicist who planned and built the Google quantum computer based on superconducting qubits that demonstrated quantum advantage and, in fact, triggered the expectations that we are living now. So welcome, everybody, and thanks again for being with us. So let me start with a question, and then the format is that we can just talk to each other and just interrupt, like if you were sitting on a Stammtisch, and just can go in any direction you want. So but let me start just putting the first question. So regarding the present situation in quantum computing, is the euphoria that we hear in media, in industry, in universities, everywhere justified? So who wants to start? Just unmute yourself and just start.
I'll start and talk about that. You know, the concept of quantum winter, I first kind of encountered about 10 years ago when, you know, people were working on qubits and doing that, but we were just beginning to build systems and people were wondering whether anything would happen. And, you know, of course, you're always worried about that. And, you know, now that we are building big machines or bigger machines, you know, it's also a worry. But I guess I would say it's at least an advance right now when we worry about quantum winter, that we're that much farther along, and one could maybe see that there is potential to build a powerful quantum computer. So that's good, but maybe the expectations are higher, and thus we have to worry more. One thing I always try to say, and I don't know if the message gets out because there's a lot of hype about this, is that building a quantum computer is hard. And, you know, we don't know in the end if we can build, say, an error-corrected quantum computer or even build a use for algorithms. Certainly, we can do powerful algorithms. We'll do something useful. But you know, the research is far enough along, so there should be substantial investments, and we have to try. And we just have to see if we can do it. So I think it's healthy in that regards. But, you know, with getting the funding and getting the money to do this, you know, we kind of have to deliver next. That's our job, or at least that's what we have to try to do. Thank you.
I could go next. So I think that what the experimentalists have managed to do over the last 20 or 25 years in going from, you know, one or two very noisy qubits to, you know, the achievement of quantum supremacy, quantum advantage, whatever, over the last year or so, you know, has been extraordinary. You know, I think things are further along than where I expected them to be by this point. You know, obviously, you know, we're not at fault tolerance yet, but, you know, if you just compare where the systems are now to where they were, you know, 10 years ago, 15 years ago, I mean, it's been astounding progress. But now you asked, Ignacio, whether, you know, the euphoria is justified. And now if you look at the euphoria in the popular press, right, you see things like, you know, quantum computing is, you know, going to cure cancer, it's going to solve global warming, you know, it's going to be as significant as classical computing was, you know, in revolutionizing society. And, you know, I think that we have sort of known from the very beginning of this field since the 1990s that the reality of it sort of, you know, has a hard time living up to that. You know, I mean, anything would, right? But we have understood since the 90s, really, that the applications of a quantum computer, are extraordinary. It's extraordinary that you can beat classical computing for anything. But they are more specialized than some people in the popular press would like them to be. And I think that remains the case. There are lots of exciting developments in quantum algorithms and on the theoretical side, but I think nothing that has changed that fundamental picture that we've had since the 1990s.
Yeah, I can only agree with what Scott and John said here. There's a certain hype at this time, which of course is made from some of the success stories that we've had. And this, I agree with John and also Scott that we have really made some very good progress over the last 10 years and so on, and even more. This is fantastic. But the expectations, of course, are in the general public are usually very high, and we certainly will not be able to match all of those expectations. On the other hand, this demands more that we are honest about what we can do, what quantum computers can do, and where real solutions might lie in the future. And we should not exaggerate what the quantum computer could possibly do and whatever. So we should be really honest with everybody. And I agree, then the quantum computer has a bright future. And I'm absolutely sure that this is going to lead to something very useful, even if the quantum computer, as John says, would not be able to come forward with, say, an error-corrected, fault-tolerant version. But in the long run, we will learn so much from it, and we will really get a lot of profits from that in technology, in measurements, in whatever communication, that this is absolutely worth every effort.
Yeah, I want to say that the word euphoria is even more questionable than I think Scott was mentioning, because we don't really know how. I mean, this is a very, very powerful thing that is being developed. And A, we don't know what are the good things that we will be able to do with it. But B, we don't know what are the bad things we will be able to do with it. And it seems to me like the excitement is very, very justified, very well justified. It's really amazingly exciting theoretically and conceptually. But what exactly is everybody excited about? This is really sort of, it's not clear, right? Everybody is excited because everybody is excited. Are we talking about a specific problem? Like, are we thinking of curing all the problems of the world? This is not what's going to happen. And even not, curing all medical problems of the world or stuff like that. What are people excited about? If you really ask, that is, I think, a very big question mark.
Maybe I can try to add a little bit, and it's kind of partially maybe answering or, kind of maybe putting this a little bit of a positive kind of spin on this kind of direction. So, certainly as John kind of said in his first, kind of few sentences, it is kind of, you can, take a step back and look at all of what happens and you say, well, look, it's shocking because, all of these things, all of this hype is going around, but at the same time, we do not know right now, if and how we can build truly, large scale machines. And second, we don't even know if we were to build one, we are not sure exactly what we could use this for. So you could say, what is there some substance, in kind of all of this excitement, or is it all, kind of superficial? And I would say there is kind of an aspect in which these times for which we are living kind of in this quantum era are kind of special. And the aspect in which they are special is that we are now kind of starting to build machines which are kind of large enough, coherent enough, programmable enough, such that, we can do things that, classical computers, have hard time doing. And, that actually is an opportunity for us to really start thinking, using them to try to build even bigger machines, maybe discover, more efficient, better ways to do quantum error correction, to do, all of these great ideas of topological protections, right? Kind of things like this. And at the same time, I also think that, these machines, which we are now just kind of, starting to build in a lab, already allow us to basically, kind of go in the domains, where no one has ever been. And I would say for scientific applications, I think this is a very special time. I kind of sometimes call it an age of quantum discovery. We can do things, for example, certainly in the domain of like non-equilibrium dynamics, we can do things which, no one has even tried to do numerically, and, there, basically, whenever you go to these kind of domains, you start making discoveries. And I think, in the near term, that would be, I think, at least, I personally am most excited about these kind of things, like scientific payoff. And I think that from that point of view, it's a very, very special time, so.
The whole language of science is changing as we speak, right? The whole, what is an experiment? What is what can we do and what we can't do? What does it mean to understand physical systems? The whole thinking of science.
Dorit and Misha, this is the excitement among us as physicists.
Yeah.
But now you're talking to the people, to the lay persons in the field. And they get excited when they hear computer and all the progress they have made over the last, say, 10, 50, 10, 20, 30 years with computers. And they expect now to have the same step forward with quantum computers, which is not going to happen. You have to tell them what our excitement is about. So you have to really do this in a different way. And you have to tell them what can eventually be the excitement. And there's going to be enough that we learn from that maybe 20 years down the road, but not quite now in the next 4 or 5 years. And this is something we have to be very careful about.
But I mean, to me, go ahead, Scott.
No, okay. I mean, one of the most common themes when I talk to journalists about quantum computing is, disappointment when I have to break it to them that I don't think they're going to have a quantum computer in their pocket, anytime soon, right, or a quantum iPhone, right? But then I sort of have to debug all of the thought processes that led to that hope. Like, okay, why did you want a quantum computer in your pocket? What did you think that it would have done for you, right? That your existing phone does not do? Do you have a great need to, simulate physical systems, to factor integers, when you're on the go, right? But furthermore, supposing you did need those things, why not tap into the cloud, right? I think this is one of the biggest things that people get wrong, that sort of this time around, classical computing already exists, right? Which means both that quantum computing is only really useful, only benefits us for those special applications where it beats the best that we can do with a classical computer, right? But it also means that we can take advantage of our existing classical computing infrastructure for everything that it can do, and then use the quantum computers only where they're actually needed, only where we have to use them. Okay, so it's going to be different, from the original, silicon computer revolution, for that very basic reason.
But if you explain it that way, does that stifle the excitement of a layperson?
It's strange because, often I will, say all of these, maybe deflationary sounding things, and they'll nod along, and then, at the end, they'll be sort of just as excited as they were at the beginning. Which I like in a way, because, I'm excited even, for the scientific reasons, if for no other ones, right? And I would like others to also be excited about it, but I would also like people to have a clear understanding.
Absolutely, yes.
Yeah.
So we all agree on this. So it's not.
We all agree on that. Yes. So, but there is a lot of expectations now, at least in Germany. Probably that Germany has now devoted a lot of money, actually, $2 billion basically the next 5 years. And it's coming from the industry, not for the scientists. Scientists are very excited, but the industry is even more excited. And they are really thinking that, first of all, that they will solve the problems there, batteries for cars and whatever. And on top of that, when you tell them, well, we don't know how to do that, they say, well, you scientists are scientists. Give me that. I know how to be an entrepreneur. I don't know how to do that. And it's a bit dangerous, or not, or maybe they're right and they have to do that, and maybe that's something coming out. So what do you think about this attitude that they have?
Scott, are you going to give the NP spiel?
Only if I'm specifically asked to. No, I look, as the title, like right beneath the title of my blog, for many years. I just had, look, quantum, if you take only one piece of information from visiting here, quantum computers will not solve hard search problems magically by just trying all of the different solutions in parallel, because, that's a misconception that arose so often in conversations about this topic. We're really talking about a very special hammer here, a special way of exploiting nature to solve computational problems that involves this constructive and destructive interference of amplitudes, right? And it's a minor miracle that there are any interesting nails at all that this hammer can hit, right? And so I think that sometimes we're a little bit like in the story of Rumpelstiltskin. We're like, ungrateful for Grover's algorithm and Shor's algorithm and, the amazing quantum algorithms that have been discovered. And people say, well, they want it to be more than that. But I think that, what it can do is already pretty extraordinary.
Actually,
But,
Scott, sorry.
There are sort of three entities involved in this. The scientists, who I think are extremely justifiably excited. The industry, whom I think is not, they don't maybe know why they're excited, but I think it's highly justified as well. I mean, I think that that even though, okay, we won't be able to solve NP-complete problems with quantum computers, I'm sure that we will be able to solve so many things that we don't know yet once we have quantum computers. I think the industry is very right in its being highly excited. The third entity is humanity, is other human beings. And that I think is much less clear, why they are excited about what the effect will be on society. And this is unclear, I think. But for the industry, I think that the excitement, the effect of, the more things that we can do is obvious. It will happen.
But this is actually what worries me a little bit, because there's excitement in industry because the expectations there are very high. But then you're talking to people, possibly applications, and they applicants, and they actually are asking me, so what can I use my quantum computer for? Where are the algorithms that really fit my specific purpose? Goodness, so I'm a little bit at a loss. So my question is, how can we go for more and better algorithms? Where are the corners that we have to search for in order to get, say, better ways of using our quantum computers, provided we have one? I'm sure we will have one at a certain stage. I even believe that we get to the fault tolerant level. This is not clear, but I do not see any basic hurdle, any fundamental reason why not. But then the question really is, what are we going to calculate?
So maybe I can add to this a little bit. When I was at Google, the theory team was trying to talk to some of these industry people, like you mentioned. Industry is getting involved. And kind of the idea there was, yeah, they obviously want to say, what can we do right now? But the idea there was to work with a few people, not everyone. You're not trying to make money on this. You're trying to get a few people and then try to get the industry to have a small group of people who are quantum savvy in their company so that they begin to understand what's possible with the quantum computer, and then start, kind of playing with the algorithms or whatever hardware you have to gain experience in it. Because part of the problem is, yeah, industry's interested, but they don't quite know how to use it. And we don't have like Reiner said, we don't have a clear story to tell them. So I thought it was very healthy for a few companies to just start a small quantum group and work with universities and work with other researchers to try to figure out what's going on. And I think, I think that's a very healthy development. And we have to see where that goes and what kind of results you can get out of that. I certainly think it's bad to oversell what a quantum computer can do, and good to work with them, companies, on a scientific level, and try to build up the knowledge of everyone. And partly you want to build up that knowledge. I think industry will understand that okay, maybe now we can't do something, but if some discovery and someone figures something out, Then if you have an internal group and an industry, you'll be able to know what to do very rapidly to then turn it into something useful for the company. So we all need just to gain expertise so that we can take advantage of developments well.
John, I've made exactly the same recommendation to people at big companies that, you want 1 or 2 people who really understand the subject and who can keep you apprised. But I have a position on quantum algorithms that makes me unpopular with some people, which is that, I think that a lot of low-hanging fruit was picked, in the 90s. And, Shor's algorithm, Grover's algorithm, these are fundamental primitives that were discovered very early on. They have lots and lots of generalizations and applications, but, it's been hard to discover more. And, I feel like when you're, in an orchard where the low-hanging fruit has been picked, you could keep leaping for higher and higher fruits, which in this case might mean quantum algorithms for graph isomorphism, for lattice problems, for NP-complete problems, approximation algorithms, things like that. But in the past, usually a good strategy has been to just look for new orchards, look for places where people have not even been jumping yet. And I think that that's where to expect the most success. Of course, if I knew where those orchards were, I would be going to them.
So maybe actually I could add a little bit, maybe slightly disagree with Scott, and it's kind of going back to this this kind of point we discussed earlier about this kind of age of quantum discovery. So while of course most obvious kind of directions would be really scientific problems, quantum simulations, dynamics, and so on, I do believe that with these kind of machines, which are now we are starting to realize in our labs, maybe, going to, sort of around 100 or so, or a few hundred, possibly, qubits, we are now in position to really start, trying, kind of much broader classes of algorithms which have eluded, rigorous theoretical kind of proofs and so on. And, in that regard, it's kind of useful sometimes to look at the history of kind of classical computers. And okay, I'm by no means an expert, but from what I understand, people told me is that, and at the time in like 1940s and maybe 50s, when the people started building kind of larger and larger scale classical computers, they had certain preconceptions. There were some algorithms which people thought will be efficient and will work well, but there was some other that people really did not know, how well they'll work. And then they tried them, and then the algorithms which were supposed to work well, they kind of worked, reasonably well. But then there was some other algorithms which they just discovered almost by experimenting, which worked extremely well. And then it took 50 years to understand and prove, how well they work. The more recent example of that are the deep, kind of deep neural nets that people still don't understand why they work and when. So I hope very much that, within next, I think, well, maybe I would say one kind of next year or maybe next few months, we will be in a position with quantum machines such that we can really start trying these kind of things, right? Trying, optimization, sampling, quantum computers must be good in sampling. There must be some useful sampling.
But I think they're not so dire. I mean, you're talking as if we don't know at all how to use, like what algorithms we will be able to use, and we'll have to just search and wish for some luck. It's not the situation. I mean,
I did not mean to, but it is. I do think there are some real opportunities which.
I agree with you. I agree with you. I think I agree that we don't know. I mean, the humble position is we don't know, and probably we will find new things that we still cannot expect. But we should understand that we cannot expect to solve the hardest problems, like NP-complete problems, but I think we should be able to expect already now that problems related to chemistry and to pharma, quantum computers will be able to do a lot about, because this is sort of their game, the ball game. I think that about problems like optimization, and things that in the worst case are extremely hard, we should be very wishful thinking. But I agree that there are chances.
There could be, for example, So, for example,
I agree with you. That's my point.
There could be classes, for example, optimization. I could imagine that there could be classes of problems which are kind of more amenable to quantum speedups, and which are less amenable without breaking any of this computational complexity here, right? These are the kinds of things we want to learn, look for, right? Yeah, sorry.
Yeah, let's go back to much simpler things. I have a view that if we provide, say, toolboxes, little quantum computers to the public, to people, to young people, to engineers, and let them play with something, they will come up with solutions for problems that we have never thought of. A few years ago, I was in the UK, member of the scientific advisory board, and they had in their team a young student who was doing Masters of Business Administration, and they were trying to figure out, so what is the best use of a quantum computer in the future, and see what can it be used for. To my surprise, this guy, who was not a physicist, he was an economist, he came up with quantum games. Apparently, quantum games, there's some teams and some software companies that are mimicking quantum mechanics on classical computers because game people really want to have it. And I'm sure once we can provide, say, small systems, we will find all kind of applications, not necessarily these high-ranking things. So I think it's going to be a bright future in that way too.
You mean like robot tricking, like
whatever?
Kind of
I don't have the slightest idea what it could be used for. I'm sure.
I have tried to play a couple of quantum games, or what were billed as quantum games. I found them utterly confusing, which maybe was the point. But look, I want to say,
did you lose, Scott?
What? I think
the games in quantum.
Yeah. No, I mean I think it would be great to have games that would be pedagogical tools to teach people quantum mechanics, but the games should be less confusing than quantum mechanics itself is, not more confusing, right? That seems to be the hard part. But Misha, I think you are absolutely right that some of the most important algorithms were discovered by empirical, just messing around, and that will probably also be true with quantum computing. I mean, that's already happening to some degree right now. The hard part is that this time around, it is not enough to show that your algorithm works or that it's fast. You have to show that you can beat the best heuristic that anyone can do with a classical computer, right? Which also doesn't have to be rigorously proven. Yeah. I think that's really the tricky part.
Yeah, no, but that's great. I mean, that's an exciting challenge, right?
Yes, absolutely.
Maybe the outcome of that we will improve classical algorithms.
Yeah.
I will take that. So right,
yes.
So that's
Yeah, no, I mean there were already some examples.
Where that absolutely, yes, exactly, yeah. And hopefully there will be more, right?
Yes. Yeah.
So once we have reached this point, I think that we are getting excited about the quantum computers more and more. So if you had a lot of money to invest, so in which would you invest? Would you invest? I guess that's very clear for some of you, but in a quantum computer, to build a quantum computer that is scalable, maybe a NIS device that goes up to 1,000 qubits, maybe in algorithms, maybe in the industry, maybe in the pharma industry, like you say, Dorit. So what is one bet that you think would be, in your case, kind of a secure bet, or one that you would like to bet on?
GameStop, but a few weeks ago. I don't know. I feel like if I were able to place bets, I wouldn't be an academic. I would be.
Very good. Michel?
So are you asking about kind of specific?
You have 100 million of whatever currency you want. You want to put it on something on quantum. What would it be?
Yeah. So I think the most kind of, I think this area is kind of very special because the kind of cutting edge kind of academic fundamental research, kind of converges with like, super advanced engineering, and also with this kind of application angle. So what I think is the most exciting, and, I don't even know any other area of science where these three things would really kind of converge. So to me, that's maybe the most exciting and most promising kind of avenue. And, true, the first examples could be scientific applications, but look, for classical computers, the first examples also were scientific applications, right? There is no kind of, I'm not ashamed of that, but I think that's this interface, which is, I would say, the most kind of promising for and fruitful for investments.
John or Rainer or Dorit?
Are you asking me now as a,
yes,
as a businessman, say, for a company, or say as a scientist, or just a layperson?
As a businessman, you want to make money.
I want to make money. We have been discussing this among ourselves for the last 2 or 3 years without disclosing too many details here, but I can tell you this is a very difficult story, and it's really, where do you make money? I'm sure we are not going to make money for the next 5 to 7 years to come, unless we have more to deliver that really solves some of the chemistry problems which are interesting to industry right now. But on the other hand, as I said before, I really would bet if you have, say, small-scale quantum computers available and provide them to industry, provide them to schools, provide them to universities, provide them to everybody, not very expensive, maybe 50, maybe 100 qubits in the not too far future, NISQ devices, then people would get a different attitude. They would just try these things out. They could learn how to do this, and they would, as I said before, I'm very sure they would come up with applications. They would come up with ideas and algorithms that we do not dream of. So my bet would be providing hundreds, if not more, of small devices, quantum devices. And then, of course, something that is usually forgotten about all the hype of quantum computing is that the technology, the underlying technology, can be used for so many other things. My personal point of view is that most of the use of the money that will be made, not by the computation, not at least at first, maybe in the far future, but in the not too distant future, I think companies will make much more money using them for precision measurements, for enhanced measurements. And we have seen already some of these things. Some of these devices are sold at this time relying on older technologies, like just what we call the first quantum technologies, which are now coming into play. But there are already upcoming devices that rely on entanglement and improve certain measurements. And here I see a market. I definitely see improvement for clocks. I see improvement for precision measurements, forces, masses, whatever there is. And I think that is a market that is underestimated at this time. And too few companies see it. So we have to demonstrate that first.
So I think that if you, the question can be treated as maybe next 5 years or maybe next 20 years. In next 5 years, I would actually put my money on things that deal with how hard it is to build quantum computers, because it's going to be very hard, and everybody who is actually managing to help those and overcome those difficulties will be worth a lot of money. In 20 years, you're basically asking, okay, where will humanity be in 20? What will be the most interesting things for humanity in 20 years? And this is really, a very, very big question. Maybe quantum deep learning, understanding superpositions of human beings. I don't know.
What is quantum deep learning?
I have no idea. I just invented. I'm after half a beer of.
Okay, good. We're going in the good direction. Very good. John?
I wanted to add, if I may, it's kind of like $100 million to invest or whatever is too little money. Okay, that's kind of the problem, in the sense that there's a large number of things to do, a large number of systems. And you can't predict where everything is going. So but when I say that, there's already much larger than 100 million being invested in the field. And I think that things are actually kind of quite healthy now with the wide range of government and industrial investments to push forward things, and then we see what happens. And of course, there can always be more and better and whatever, but you know, the field is not that bad right now because of that. Now, in terms of, well, okay, what for $100 million, what would you do? I kind of like the idea that Derek just said, you know, investing in things that you're going to solve the problems and build a quantum computer. And that's certainly how I'm thinking. And I certainly, you know, in superconducting devices, I think there's a very good future and would do that. But, you know, I think all the other technologies are quite interesting too, and you would have compelling cases to do that. So I think we're in good shape here, and that, you know, there is enough funding available that, you know, the field is getting pushed forward. And again, we're kind of waiting for something to happen and see what might be, you know, the first useful and financially useful application. And of course, that will be a big change in the field.
Okay, perfect. So we are going to have questions from the audience, but before doing that, I wanted to ask you a question to each of you. And so the question, if you had not been a quantum scientist, what would you like to have been? So what else could you have been? Okay, let's start with Dorit.
Okay, I would have been, I don't know if you guys know Jane Van Leeuwen Godel, who was a researcher of chimpanzees in Africa. So I would have been her assistant. Instead, if I weren't a quantum computing scientist, that may be what I would have ended up in. Maybe I will.
Okay, very good. Misha.
I don't know. I wanted to be a filmmaker, you know, as a
Filmmaker.
Yeah, prior to my kind of physics studies. So maybe that's what I would have done. It is also interesting time there.
Yes. John?
Well, I'll answer it in the physics sense. I was enjoying a very nice career making ultra low temperature particle and radiation detectors in the early 1990s and then through the 1990s, and was very much enjoying that as a way, you know, to build practical instruments. There were special purpose scientific instruments, and I found that really fascinating and great. And it was only because of the advances in quantum computing and the idea that, you know, maybe you could build a quantum computer and it could be useful and powerful that kind of sucked me out of that old project and into something that turned out to be even more interesting. So so that's all been great for me.
Rainer?
Initially, I wanted to become a musician, but then it turned out I was not good enough. And then I wanted to become a sound engineer. And some people really convinced me that you had to have an absolute pitch, which of course is ridiculous. In the end, I decided to become a physics teacher for mathematics and physics and ended up to be a quantum physicist. So it was somewhat.
Scott?
Well, at some point, I wanted to be a novelist, an essayist who's, you know, writing would awaken the whole world to the power of reason. But I think I realized at some point that building quantum computers or, you know, solving P versus NP were actually easier problems than that one.
I'm not sure about that.
Okay, so we have here some questions from the audience. Let's start with, okay, so are quantum engineers or quantum software engineers needed?
Yes. Definitely, I think this is one of the biggest problems, if I may answer. Right now, we have already established at the University of Innsbruck a study of quantum engineering. And this is not really halfway engineer, halfway physicist. It really is something new, a hybrid study, where you really tackle problems, engineering problems with a quantum point of view. We face the problem right now all over Europe, and I think this is true all over the world, that we have fantastic engineers who know their job really very well. And we have very, very good, bright physicists who know their job well. But getting them together and having that knowledge in a hybrid way is usually very rare. And this is the kind of breed that we need for the future.
Yeah, and what happens with quantum engineering is that you have to study the engineering discipline a little bit more like a scientist than a conventional engineer. And training people to be both a scientist and an engineer at the same time is difficult, both for scientists to think like an engineer and an engineer to think like a scientist. And it almost just requires people with a certain skill set. Now, there are a lot of people out there, a lot of engineers who do that, scientists who think like engineers. The other thing I would say is one of the things we have to do as physicists is try to figure out how to explain what we're doing in a simple but useful language so that engineers can understand what we're doing. Just explaining, Hamiltonian physics or whatever may not be good enough for engineers to really grasp problems. And it means that we have to think about new ways to explain things. It's just like you had Maxwell's equations, and Maxwell equations were not enough to understand how electrical engineering works. You had to develop a lot of mathematics and concepts to do that. And I think we have to do the same thing as physicists, is to be more creative in the way we talk about quantum.
Let me move on maybe to, Misha, wanted to say something?
Yeah, so I think it's maybe to think about it, it's also worth going back to the past and remembering that, like a long time ago, electrical engineering was the, part of physics departments, right? And then, or computer science was part of mathematics department. So I think we are kind of at the same, almost could be called inflection point, right? Where this quantum engineering should come out from kind of several of those existing disciplines, right?
Okay, so maybe a question for our computer scientist experts here. So it says, since we expect future quantum algorithms to emerge mostly from heuristics, should we temporarily relax the requirements of trying to beat classical algorithm? Else we'd be ruling out things too soon. So what do you think?
Well, I mean, first of all, I'm not sure if if the presupposition is even true. I mean, I hope for progress in heuristic quantum algorithms. I also hope for progress in, rigorously analyzed quantum algorithms, right? And it's hard to predict what will beat something else if you're basically just waiting for some spectacular surprise to come along. But I mean, people certainly do what the questioner proposes all the time, right? You can look on the archive, on the preprint server, every day, and there will be quantum algorithms being discussed, even though there is no evidence as of yet that they beat classical algorithms for anything really, right? There are just dozens of papers like that every week. So people are not. I don't think there's any problem of people sort of being suppressed by that right now. The issue is, I'm typically, I would just based on our past experience in quantum algorithms, I would rather have a small quantum speed up over classical computing, but that I'm really, really convinced is for real, even if it's for a not so useful problem, than than addressing the most useful problem in the world, but not clearly getting a speed up for it. Because I feel like the former, once you have any speed up that's really for real, then you can work with that. You can sort of adapt it to new situations, right? But there has been a lot of effort, into sort of, let's just take deep networks and add quantum to them and see what happens. Let's take genetic algorithms and add quantum to them and see what happens, right? And it can just go on for arbitrary amounts of time, without sort of, often, even if people won't be claiming that there's a speed up, but they'll just be, it seems to me, kind of avoiding the question, right? Like you ask the question about is there a speed up? They literally just change the subject.
Well, it depends on for what purpose, right? I mean, so for physicists, of course, this is very useful to run quantum algorithms that do classical things in different ways, and just to see that these things, for experimentalists, of course, this is extremely useful. If you want to discover new ideas, basically, this is what we're looking for, right? Seeds of new ideas that can grow new algorithms, just like the original ideas that Scott was talking about the low-hanging fruit. And this is, we don't care if it's small speed up, or we want to understand what is the structure that quantum computers can exploit that classical computers cannot exploit. And anything that increases our understanding, and that is welcome.
You said that better than I did. Thanks.
Okay, so there's a question, an interesting one. So what is your favorite beer or wine or snaps or drinks, let's say in general?
Depends on the time of the day.
Okay.
I mean, it's funny because I just had to answer that exact question for this Stammtisch. I was asked what drink I want, so I said Bailey's Irish Cream. I don't know.
Okay.
I like it, so I just drank a glass of it, which I hadn't in a long time.
Okay, Dorit. So they say the optimal with respect to all times of the day, of the maximum.
Spanish red wine, like
red wine. Very good. Which wine? From where? From Israel?
Spanish red
Spanish. Oh, wow. That's good. Okay, Rioja. Very good. Rainer, I think that's.
Yeah, I would side with Dorrit here. I really love red wine, and I love all kinds of good red wine. So various areas I could go with a very good Californian, Italian, Spanish, French, whatever, but a good one. And this one is really an exceptionally good one. Thank you very much for this.
But Rainer, I thought that you're a specialist on schnapps.
Yeah.
I never understood this,
I was going to answer that, so I think Rainer's neighbor schnapps.
Before you actually say something, Misha.
Exactly.
I have a good friend who makes schnapps in our local village. He was with me in a wind band, and we are very good friends. He's a local schnapps maker and one of the very best in the Tyrol. I didn't drink schnapps for 20 years before I came to the Tyrol, and I was seduced essentially by him because I was made welcome in the wind band, and I had to drink a little glass of schnapps, which is fruit schnapps, apple, pears, plums, you name it. And I have maybe one at the weekend, maybe two at the weekend. That's about it. So I would not side with Misha, who really makes me drink vodka whenever I visit him.
Okay, so Misha?
I think the Rainer's, neighbor schnapps is very high on my list. I must honestly say that, and it's quite exceptional. It's very special.
Indeed.
Yes.
Any preference, John?
I'm going to say, while in Australia, the tea, of course, is very good. But what I'm really missing right now is good iced tea, which is they serve in the United States.
I see.
So
They don't have that?
understand the concept of iced tea in Australia. So.
I see. Okay, let's go back to some other questions here. So we said here that how do you see the academic system forming incentives to actually interact with the private sector and or industry in a way it will benefit their academic career?
What?
I repeat it. So how do you see the academic system forming incentives to actually interact with the private sector and or industry in a way it will benefit the academic career?
I'm going to just say that now that complex quantum systems, quantum computers are being built and companies and other people are putting it online, I think this is a really good opportunity for people in the university to use a real quantum computer. And of course, there's the educational component, but also there's going to be a strong research component too. And of course, as we've been discussing, maybe some of the discoveries will come out of that. So I think that's a very good trend in the field. And I think that's going to be more and more important and more useful over time. And we're just beginning to see that right now. I think it's going to be really exciting in the next 5 or 10 years to see what happens there and see, you know, the good interactions of academia with these machines.
Okay, maybe let's move to the next one. So what do you think about the future of analog quantum simulation, and what interesting problems should be addressed in this field? So Misha, Rainer, probably.
One word answer: bright. The future is bright.
The future
Right, okay.
I would go, there's all kind of spin problems, there's all kind of Hamiltonians that cannot really be easily implemented otherwise and calculated. So I think there's a lot we can do in many body problems. And we are having now 50 qubits available for analog simulations, and we are actually gearing up towards 100. And then things become really interesting.
Yeah, and the same goes for the superconducting qubits. And at Google, Pedram Rushin was working with a lot of external people to run these things. And the ability to construct different Hamiltonians, do whatever initialization measurement you want, gives you a lot of flexibility. And people, again, are still kind of learning how to use all that. And yeah, so it looks quite interesting here. And the field will go in new directions as people learn how to use the machines.
Yeah, also the question of noise in this situation is extremely interesting, because you have to map noise between different systems. And I think this opens up a really interesting deepening of our already existing sort of developing language of connections between the whole different types of Hamiltonians and different types of physical systems, and they're being connected in very, very interesting ways. So I agree with Misha again about the
to me, you know, like at least in my kind of view, I mean, if we have a goal to really kind of, you know, someday build really large scale useful machines, so there are kind of many different paths to that. And let's say kind of gate control, you know, devices, you know, is kind of the path where we have some proofs, universality, we have at least conceptually ideas that we could do error correction and so on. But in practice, it's just one path, right? There are all sorts of other paths, right? There is a measurement-based quantum computing. You know, there is, this, quantum simulation, right? And to me, actually, analog and digital, the boundary there is kind of a little bit gray, right? And, you know, if you have, but, you know, once you have fully programmable quantum simulator, it's as good as a,
universal quantum computer.
Yeah, that's as good as any other machine. Perhaps it's even better than a gate control, strictly gate control machine, right? So that's kind of, I think, you know, and I think we need to explore all of these paths and kind of aiming in particular at really sort of, you know, focusing on useful quantum advantage, where we could really solve interesting problems, scientific or beyond.
Somehow there has been a little bit of a clash in the past between computer science and physicists. Physicists trying to solve a Hamiltonian with 2 parameters, and just as a function of these 2 parameters, computer scientists trying to scale the number of parameters, so they didn't fit together. So do you think that this is coming now to an agreement, or that's very difficult?
Definitely. I think that it's beautifully coming out to an agreement. I think that questions like what you just said from physicists are really given deep thought and interesting answers, and sort of aspects of computational aspects of those questions are really being revealed in this area. I think it's beautiful.
Yeah, but also I think also, sorry, Scott, so that to adapt, even sort of adapting the language of computer science to some of these less trivial kind of systems, and you know, I think it's a super fruitful direction where I think a lot of things, you know, we can kind of discover. Sorry, Scott. You know,
No. I mean, since I started, you know, giving talks about quantum computing in the early 2000s, so you know, one of the main sources of humor, you know, that I mined was, you know, the difference in culture between, you know, computer scientists be like this, physicists be like that, right? And you know, and there are different assumptions. And I feel like that's gotten harder, right? It's gotten, I have less material because, we've learned each other's languages so much better than when I started in this field. And, now, any computer scientist who's doing quantum computing, knows what Hamiltonians are, knows what fermions and bosons are, right? And, the physicists, certainly, the ones who I talk to, they know what P and NP are. They know that NP doesn't stand for not polynomial, they know what non-determinism means, right? So, and even, often even much more sophisticated things than that about, approximation algorithms, PCP. So, I feel like, in terms of, forming a new field of sort of computer scientists, physicists, mathematicians, engineers who all speak each other's language. I mean, quantum computing has already been a success, right? The actual devices, will just be a cherry on top, right?
Very Okay, another question in a different direction. So for fresh graduates, what would your advice on staying in academia or going to the industry at the moment?
Depends on the person. Yeah.
But after graduation or what? After PhD?
Fresh graduates, they say.
Mm-hmm.
So it's not a general formula.
No, not at all.
But has it changed in the last 5 years? Like, let's say that you would now advise more people to go to the industry than before?
There are opportunities in industry that now exist that did not exist 5 years ago. So in that sense, yes.
Mm-hmm. Okay. So maybe another one. So can you remember one time during your research career where quantum mechanics really confused you? And I think that Scott has a very nice quote that if you take out physics out of quantum physics, then it's very simple, no?
Yeah. Well, I mean, the context was that, you can think of quantum mechanics as a generalization of the rules of probability themselves, and then in some sense that is what we do in quantum information, right? We think about it abstractly, not tied to a specific system like photons or electrons. But, it's still confusing there. I mean, there are different ways that something could be confusing, right? You could be, confused just about how to do the math, or you could know how to do the math and, be confused about what it means philosophically or something like that, right? I think at a certain level, all of us are confused about it every day, right? But, it's a good kind of confusion. It's the confusion that sort of drew us to the subject in the first place, and it keeps it interesting for us.
So anybody?
Yeah, I wanted to just add that I got interested in qubits as a graduate student and later as a researcher, in part because I wanted to understand how quantum mechanics works better. Okay, and you can take it in your classwork and solve problems in it, but by building systems and using it, you get a very good sense of how it works. And it's kind of reminds me, one of the reasons I like going into physics is I could see the world around me and build things or whatever, as an amateur high school student. And then by going into physics, you see how it really works. And of course, it's very hard to do with quantum, but when you're building a quantum computer, you're seeing what it does. And then, you can really get a very intuitive, deep understanding of how quantum mechanics works. And of course, it's very beautiful to do so.
So what about the other? So any thoughts?
Confusing part for me was not so much how it works in the end, because once you do experiments with that, you get used to it. So, but getting used to it really means, okay, I understand this. This is what we usually mean by understanding. But when you think deeper about it, what do you actually understand? You know how it works. You know how these things get together. But the confusing part for me was always, we have some strict axioms on which the entire mathematical framework is built, and we use it, and we shut up and calculate, as Dave Mermin would say. And yes, that works. So the confusing part is then generally the part where it becomes non-local. And this is still confusing to me. So entanglement per se is still, and John knows what I mean when I talk about entanglement, because we had some discussions about this. But entanglement for me is still, I wouldn't say a riddle. I understand how it works. But you know, I have a hard time really getting used to this notion. And I understand the discussions they had in the 30s and later on, and also these interpretations of quantum mechanics. This is where the confusion can set in. And I, for myself, have not solved this problem, except for the fact that I just I shut up and calculate, and this works perfectly well.
So let me say at this point that we are planning a quantum Stammtisch on the foundations of quantum physics. So I guess
wonderful. I would love to see this.
Yeah, okay, different. Okay. Dorit?
I want to say that for me, this is almost a physical feeling. This mind-boggling that entanglement raises. It's like it's the lack of understanding of how things fit. To me, this is the most fun part and the most interesting part. But it's also almost physical in how it affects the brain.
No,
this mind-boggling part.
Sorry, physical is what I can do in my lab. I have a physical way of doing this. I can play with it. I can make it. And the question is still, think of it.
No, I meant that I feel it in my body.
Okay, I'm not sure I can feel entanglement, but I would love to.
But so, you know, at the end, this confusion is probably a good thing, right? Because if it forces you to think about things kind of more deeply, right? That's our hope to to figuring out a useful quantum advantage, right?
Sure.
That's what it is, right?
Another maybe interesting idea is, as Reiner was saying, in the end with quantum, you shut up and you calculate, okay? And then, you know at least what it's going to predict. But as we're building these new quantum systems, not systems that are in nature and then you're describing them, but we're trying to invent new ways to put them together. It kind of expands a little bit what you're thinking about quantum mechanics, and forces you maybe to think about this in a different way, and forces you to be inventive about it. And I think that has been interesting for me, is to just think about it, maybe you might even say from an engineering point of view, is an interesting exercise too.
And it's, by definition, quantum advantage is about things you cannot calculate, right? So being confused and I'm sure that new intuition, I think it's very important to have, intuition, but this will be, kind of, hopefully the discoveries we'll make with quantum computers will sort of stimulate new intuition about particular things like many-body kind of systems. I think that's maybe hopefully one of the lowest hanging fruits, right?
So let me ask another question here. I will translate it. I'll change it a little bit. So do you know any problem that it's, let's say, not academic, not to prove quantum advantage, but the problem that could have any use, that could run in a NISQ device faster than in a classical computer, even, let's say, for 100,000 qubits? Is there any that we know?
I think that the best shot for that is quantum simulations.
Well, apart from quantum simulation.
Apart from that, I have a proposal that I explored a couple of years ago, which was, using a NISQ quantum computer as a sort of source of certifiable random bits. There's, random bits where you can prove to a skeptic over the internet that you're really generating them randomly. Now, it's not clear if that will be useful, but we don't have a proof that it's not useful, right? And so that's something that I know that Google has explored, and that but this is a perfect example of what I was talking about before, of sort of looking for a different orchard instead of just trying to jump higher and higher in the orchards that people have been through.
A good example.
And
yes.
I hope for more things of a similar kind.
Okay, so let me change a little bit gears. We're in the last 10 minutes or so. So I want to now talk about something a bit different. So it's about ethical issues related to quantum computing. And let me just put it a little bit in context. So imagine that now there is a country or a company that has a quantum computer, builds a quantum computer, and that's scalable, and they are the only ones in the world. And then all of a sudden they start solving problems in chemistry, in pharmacy, making patents, and have all the power. So should this be tolerated, or should we do something in order to prevent something like that? Or do you see any other ethical issue that may happen in this connection?
Wait, sorry, that they would be using it for code breaking, or you
Well, no. There is only one. There is just one in the world, and then they have the whole power, because I mean, all of a sudden they can use it to solve problems. I mean, to break, let's say, cryptography, but also to patent. I mean, all the patents now they get because they can use it for medical drug.
I mean, I feel like one could ask that about any technology, right? There's nothing special about quantum computing here, right? People could have asked about, well, what if there's only one classical computer in the world, and whoever has it, becomes a super powerful, emperor, right? And of course, that's not what happened, right? What usually happens is that, as long as people are free to develop the technology, then, over time the cost comes down. If it's something that people actually want, then, more and more people get it. This is the curve that at least that you want, that you hope for. If that's not happening, then indeed something's going wrong.
Yeah, and I guess kind of complementing that, it's more likely that this will follow what's happening with supercomputers, where, okay, there's a new supercomputer and a new leader every few years or so, but it's not that much bigger or better than the last one. But yeah, but you don't know with the new technology what's going to happen, so it's harder to predict, I suppose.
But I guess maybe one aspect of Ignacio's question is, for example, what if there is one, kind of super, machine which now can discover all sorts of, for example, useful algorithms and so on, and, or ways to build bigger machines. So, my feeling is kind of, given that we have, let's say, kind of a diversity of academic and industrial groups and also of platforms, I mean, we are kind of a little bit as a community, we are kind of in the same boat, in the sense that if we, for example, figure out that there is one specific, say, optimization or sampling problem, which is really amenable to the NISC, and if we, for example, discover it with one platform, I think this would, give a huge boost to all sorts of other platforms, which can really then engineer the systems and, kind of, probably improve upon that. So I think that, at least at the moment, I mean, given that, all of these things are very hard also, right? I think that this kind of diversity of approaches and, also of kind of various, players, academia and industry is actually quite healthy. And I think that maybe would prevent from something like that happening, what you suggested.
Yeah, I kind of find it very hard to believe that this will be the situation. But I think there are several other sort of semi-ethical questions that, like, first of all, what will be the effect on science? If everyone is just trying to search for, first of all, everyone is very much oriented by money and by grants, and more so, I think, in quantum computation research than in other places. And it's not clear whether the diversity is sufficient, diversity as well as patience, and sort of pluralism in directions. That is not clear that it's sufficiently protected in the way we're doing things now. And
so
then, of
going
course,
forward, right? Going forward, whether it will be protected, that's not clear. Right?
Yes.
And I agree. I think that's why it's important. I think this community aspect, that it's a, how people interact, and that new ideas are being kind of encouraged and not suppressed. For example, I think that's kind of very, very important. And I think
also, sorry, go ahead.
No, it's okay. Yeah.
Also, not only there are ideas that take much longer than there are certain ideas that require a few years to do research about and to actually make progress. And this is now much less people have much less incentive to go in that direction, in such directions, and that may have bad effects. So I'm not sure how exactly to influence in the other direction, but this is something that I think we are already seeing. So I don't know how to fix that.
With the earlier point, I was reminded about the like famous IBM quote in the 1940s, like we foresee a world market for 5 computers, something like that, right? Which is often trotted out today as like one of the most catastrophically wrong predictions, in the history of the world, right? But one could take a different point of view. One could say that, well, no, that the people who predicted that were actually just too far ahead of their time. Right, they were thinking about what today we would call the cloud. They were thinking about that you really only need to concentrate your computing power in a few places, like Amazon's server racks, Google server racks, right, and much of the other computation can be offloaded to elsewhere. I think that the same is true about quantum computing, by the way. That even if there were only a few state-of-the-art quantum computers in the world. They would be provided, the economic model that seems to make the most sense is that they would be offered as a cloud service. And, lots of people would be able to use them to do experiments, to do all sorts of different things.
Yeah, likewise, I would not be too much worried about that, because in the end, if anybody really wants to approach, say, a monopoly situation in this case, there's so much competition in the field. Everybody else would come up and would try to at least compete. Maybe they will not come close initially, but then after a while, there are so many competitors. I see the ethical issues here. I see the danger that there is, but I think this is a singularity that will not be reached.
Okay, very good. So I think that we will we're about to finish. So I just wanted you to say something if you want. Just anything that we didn't cover, or any thoughts that you want to share with us, and with that we will finish. So who wants to start?
Let me start. Quantum computation is a lot of fun. And I've learned so much over the last few years, and I've had so much fun with the co-workers to see this. And there are so many unexpected things that happen that I would love to continue doing this for as much as I can. And I wish everybody would just step in and join our excitement about it. Not the hype, but really the proper excitement of what could be done with it in the future. And I'm actually seeing a very bright future for quantum computing.
Perfect.
I want to say that to me, of course, quantum computing is a huge amount of fun, mainly because one of the main reasons is how it touches upon philosophical questions, like what is knowledge and what is it that we understand about nature, and the ability to actually study these things rigorously. But I think that somehow we didn't even in this Stammtisch, how do you call it? Stammtisch?
Stammtisch.
We didn't touch, I think, one question which to me is somewhat bothering, which is whether we are developing something which is maybe extremely powerful that we will be able to use, we as humanity, in wrong ways, and what should we as scientists do about it? And I think there's not enough thought going into this, and I don't know exactly how this should be structured into science, but I think it's missing.
John?
I'm just going to say that as various entities, companies are starting to build quantum systems, and they're going beyond a few qubits to many qubits, and putting them online, I think it's going to be a really interesting next 5 or 10 years to develop a kind of a user community that connects together many different kind of researchers to use a quantum computer and learn more about quantum mechanics and learn about what does quantum complexity really mean. And I think that's going to be a very exciting next decade or so as people figure that out.
Michel?
Yeah, so maybe it's kind of everything has been already said, but yeah, I join kind of John and kind of echoing his, I think this age of quantum discovery is a very special time, or kind of, if you want, discovery with quantum machine is a very, very special time. I think we are going to learn a lot, and this is this kind of time where different disciplines, ideas from different disciplines really converge. And, I really, I'm, very hopeful that this will be useful for humankind. And this is something which, people who shouldn't, who are involved in it should be thinking about, right? Should be thinking, about implications, both in terms of, usefulness of these things, but also in terms of, what kind of second order effects that, these things can, imply. But I do think that, next few years will be a very, very special time, even looking beyond headlines, just looking at, at the scientific frontier.
Scott?
Yeah, so I mean, I think so a lot of people look at where people expected us to be by the year 2021, let's say in the golden age of science fiction, and they feel like there's actually been a great stagnation, right? That we don't have flying cars, we don't have bases on the moon. I mean, we were just caught flat-footed by a pandemic, right? And had difficulties just manufacturing enough paper masks. And getting vaccine into glass vials, right? The mask.
You can't have this without even one mask now.
Yes, yeah, right. But I mean, to even be talking about quantum computing, in a world where there's so vastly more basic things that we haven't gotten right, is strange and incredible in some ways. Okay, but if like in the one area of sort of computing and communications. I think there, much of the promise of, the science fiction of the mid 20th century, has actually been achieved. We're actually living it right now, right? We're having this conversation and all in, different parts of the world. I think that quantum computing, it's something that people have invested a lot of hope in. The actual applications of quantum computers themselves. I don't know if they can bear the weight of all the hope that people have invested in this, right? But I hope that, well, first of all, that we do manage to actually build this, scalable quantum computers, and also that it will serve as an inspiration to everyone else, right? That, I would like to live in the science fiction golden age, and, if quantum computing can be one little piece of that, then that would be great.
Okay. Very good. So before concluding, let me make a couple of announcements. So first, the next edition of this Munich Quantum Stammtisch will take place in a month. Details will be communicated on the MCQST website and social media. And also let me mention that the Munich Quantum Valley, a Bavarian initiative for quantum technologies that includes MCQST as well as other academic and industrial partners, will be launched on March the 4th, and we will announce the program in the MCQST webpage again. So now let me conclude this Munich Quantum Stammtisch by thanking our guests for bringing their expertise and experience around the table and engaging in such fruitful, constructive, and open exchange throughout the last 1.5 hours. Thank you very much. It's been really a lot of fun, and hope to see you soon in person in Munich, and maybe with something like that in your hands. Bye-bye.
Cheers.
Bye.
Cheers.
Bye, guys.
All right. Well, cheers. Thank you for
Thanks a
having
lot.
us. Bye.